All right, so 6.5. So we skip 6.4. We go to 6.5, which again is another type of application of optimization. So if you remember, one variable cases, we had two ways to verify and find max and minimum values. There was the extreme value theorem, which is the closed interval case, right? We test that by finding our critical values, and we plug our critical values in our endpoints, right? In a closed interval case, you have endpoints, into the original function to see which function value is the largest and which function value is the smallest. In that case, we're guaranteed both a max and a min. And then there was the open case, where we only get one, right? That was the second derivative test, where we find one critical value on our domain. If it's concave up, it's the minimum. If it's concave down, it's the maximum, right? We use concavity to test which one we get. Well, in multivariable functions, we have something similar to that. The first example, which we did in 6.3, would be the open case, right? We use the d-test to concavity to determine if my critical values are maximums or minimum using that test to see if it concave up, concave down, turns up, turns down. In 6.5, it's the other case. It's the case where we have the closed interval case. All right. So, and there's a special method that we use called the method of Lagrange Multipliers. All right. So again, in this case, we have, instead of an open domain, meaning instead of x and y in our function can be anything, this time we've got limits, what we call constraints, all right, which means it limits our domain. For instance, we have a fixed budget, right? We don't have an infinite amount of money to spend on something. We have a fixed amount of time, right? There's only so much time in a day. You can't exceed the amount of time spent in a day. Or we can only make so many items, right? Because the machinery only allows us to spit out so many items every day. And so there's a limit to what we can do. It's called the constraint. We're constrained by the world, right? Time, money, and items. What the constraint is like I said, it's like the one variable case where we were limited to a domain. Instead of looking at the domain from negative infinity to positive infinity, we were given a limit. Well, no, I can only look between negative 2 and 5, right? And we found optimate values by taking account where we start and where we stop, right, the end points. So those could be my maximum and minimum values. Or a turning point between them, right? There are only turning points that exist between my negative 2 and my 5. In a similar fashion, in the multivariable case, we'll have constraints. Now, because multivariables are more complex, it's more formulatic, like we did with the d-test. There's something similar. We set it up in more of a formula that allows us to find optimum values of our equation within our limitations, within our constraints. And the way we do that is using the method of Lagrange multipliers. All right, which again, we do two variable functions, but it could be extended to 3, 4 multivariables. Again, as many as you want. Again, with more variables, you just get more algebra. All right, so instead of a closed interval cases, we're restricted to what's called a constraint equation, right? Because it involves both the x and the y values and usually some constant that constrains us. It restricts our variables. And so that's the first thing. Either we're given the constraint equation or in applications we'll have to find the constraint equation. And the constraint equation is where we've got some setup for our x and our y, our variables, which are limited by some k constant. Right? K would represent my budget, my time, my total items that I can produce. And so our constraint equation, we'll solve it in most cases where it's equal to, but technically it's an equal to and a less than. Because if you're thinking in terms of budget, right, I can spend up to, suppose my budget's $20,000, right? I can spend up to $20,000. I can't go over it because that's the only amount of money I have, right? I don't have more than $20,000 to spend. But technically speaking, I could spend less. If I'm efficient, I could spend less than that. So again, when we set it up, we do set it up more with the equal to. But in reality, it's an equal to and a less than. And I will do one example where we will use the less than case, right, where we have to stay less than our value. Right, again, same idea, is we can only have critical points that exist in our original function we want to optimize, or whatever our original function is, and they have to make the constraint equation true. They have to be within our limited budget, or our limited time, or whatever it is. All right, so they have to be limited to two things, our function and its constraint equation. All right, just like the one variable case had to be limited to our domain, right, within the domain. Since it involves multivariables, again, it's a little more complex than the one variable case. We actually have to set up a formula. And the formula that we use is the Lagrange Multiplier equation, or Lagrange Multiplier setup. Alright, so that's what we use. So step one is the formulation, set up the formula. Alright, so the formula involves both the original function I want to optimize, profit, revenue, cost, whatever it is, and our limitation, alright, limited budget, limited time, limited number of items. Alright, so if those two equations, either we're given the equations, we're always given the function, but sometimes we have to find the constraint. Right? And that'll be more when we get to applications. The first thing you have to do, and again, you can't just do this mentally or write it down. The first thing you want to do is usually we're given the constraint equation. We've got our x and y variables on one side set equal to the constant. Again, the constant would represent my limited amount that my x and y can be. Again, budget or whatever it is that it is. And so the first thing is we do is move that constant over, right, and set our constraint equation to 0. Right? We assume, and we also, so we do that first. And then the second thing is we assume the extreme value exists. Again, that's a fairly large assumption, but for our examples that will be true. All right. And then we introduce a new variable called the Lagrange Variable, right, in our function. It's a Greek letter because mathematicians just like Greek letters. And so it's the lambda in the Greek letter, so it's the lambda. Alright, it's lowercase lambda, is the Lagrange multiplier. And what the Lagrange multiplier is, it's sort of a check. It would be the way we'd check that we're getting the optimum value. Now, we're not going to use it, but if you do take like a higher level economics class, and the book talks about this a little bit, they actually do use the verification in sort of the error and to figure out if it's the check kind of step. Again, we don't. We just find it. That's all we do with it. All right, then we set up the Lagrange function. All right, the Lagrange function we usually write as a capital F. It's got our x and y variables and our new lambda variable. All right, the very first part of it is whatever we're optimizing. So you write down the original equation, so the lowercase f of x. And then it's minus the lambda variable times the constraint equation that we set equal to 0. So this part, the g of xy minus our constant. And again, remember, it's minus the constant. All right, so this is the setup. So again, it's an equation that involves the original, this is the original, the new lambda variable, and then the constraint. And because it does that, it's taking into account both equations. And so I know when I find my x and my y, it's an x and a y that is on my original function and within my limited constraint equation. All right, it exists in both. And then again, we do assume it's the optimum value we're looking for. There's no test in this case. It's all kind of built into the function. It's where the function comes into play. All right, so since there are 3 variables, we will find 3 partial derivatives, but again, they're fairly straightforward. The first order derivative with respect to x from our constraint equation is just the original function's derivative with respect to x. So again, you look at the original function, that was profit, revenue, cost, find its derivative with respect to x, and then subtract the lambda variable times whatever the constraint equation is derivative with respect to x. And a lot of times that's just a number. Alright, and then the y variable is the same way. You take the original function, take its derivative with respect to y, minus the lambda times the constraint equation with respect to y. Make sure that's clear, that's the y. And then the third one's actually the easiest. You'll notice in the original equation there shouldn't be any lambda variables. There isn't. It's just x and y's. And so because that's the case, those all zero out. There's only the one lambda. And so the derivative of lambda is a -1, because there's the negative in front, times, well, the constraint equation, again, is just x and y's, and x and y's are being held constant, right? And so that just comes along. It's a constant multiplier. It's an ugly equation constant multiplier, but it is. And so the derivative with respect to lambda is always a -1 times that constraint equation where we set it equal to 0. Right? It's always. Again, you can just go ahead and write that as always the constraint equation set equal to 0. Right? And then all the rest of them we also set equal to 0. Alright, so there is the 3 partial derivatives sort of again in their general format. Alright? Set them equal to 0 because again that's what we're looking for in order to find our optimum value. We have to take our first order derivative, set them equal to 0, and solve this system, right? So this would be my system of 3 equations that I have to solve. Alright, so again, it allows me to find my x and my y that exist on my original function. It is also limited to my constraint, and it is the optimum value. Right. Now, we have to solve it either by substitution, or you could use a matrix, and a lot of ours will end up being the case. Now, I'll do examples that aren't. But a lot of ours end up being the linear case, where I've got one x value, one y value, one lambda. And so I can set it up in the form, and again I have a z here, but that z would represent my lambda. Right? I have an x term, a y term, a lambda term set equal to some number, some constant, and sometimes that constant's 0. Alright, again, if it's that case, it's a linear, and I can solve with the matrix. If it's not, if I've got a square term, mixed value, or I've got some x times y, or lambda times y, or something along those lines, I can't use this method. Alright, I have to use the substitution method. And again, like I said, I will do one with the substitution method so you can see it. Most of ours will be the linear case, and you'll be allowed to use your graphing calculator for that. Alright, so once you've done, this is the hard part, right? Step 3, unless it's the matrix case, which isn't that hard. If you have multiple critical values, then again, remember, this is the closed interval case. What you do is, you take your critical values, plug them in the original. Whatever value comes out the biggest is your maximum. Whatever value comes out the smallest is your minimum. If you only have one critical value, we always assume it's the one we want. So if it's maximum, if there's one critical value, there's no test. We assume that it's built into the formula, and the formula is giving us out the correct optimum value. Right, and for our examples, it will always be the correct optimum value. Alright, so we'll go through an example. So that's the setup, and then my next video will be the example.